So in today's video, we're going to review rational functions in regards to restrictions and holes and vertical asymptotes and bring in new concepts from calculus. So when it comes to restrictions for a rational function, the restrictions come from the denominator. So when the denominator is equals to 0 and you solve for the x's, those x's are the restrictions. And when you solve for the zeros of the numerator, those x's that come from the numerator could be the x-intercepts. It really depends whether the x values for the numerator and the x values in the denominator, do they overlap or not overlap. So if they do overlap, it is a restriction. If they do not overlap, it is a x-intercept. And I'll show you in an example later. So in the first example, we have a rational function. The numerator is a constant and the bottom is a linear function, and our restrictions will come from the denominator. We have no zeros because there's no x in the numerator, so no zeros. However, x equals to 2 or x cannot equal to 2 is a restriction, and what that means is this is going to be a vertical asymptote in terms of what it visually looks like. Over here, we have an x in the numerator. In this case, x is equals to 2, meaning it is a potential 0, Z-E-R-O for 0. And I say potential, it really depends on the denominator. X equals to -4, so the restrictions cannot be -4. So this is going to be a vertical asymptote, but notice how these two numbers do not overlap. So what that means is x equals to 2 is a 0. Now for the bottom example here, the restrictions, it's always best to do your restrictions first, indicating what x cannot be. X cannot be 2 and -2. So these are either vertical asymptotes or holes. Now let's look at the numerator. The numerator in this case is going to be x equals to 2. And you might think, oh, x equals to 2 is a 0 because it comes from the numerator. However, notice that there's a conflict between these two numbers because they overlap. So what that means is this is not a 0. It is not a specific dot on the graph. But what is it going to be? So if you recap from advanced functions, if you notice the numerator and denominator, they have a common factor. So what that means is we can actually take this function, I'm going to put it over here, and we could simplify it. So r of x is equals to 1 over x plus 2. So the question right now is, well, what is 2? Is it a vertical asymptote or is it a hole? And there's a difference. Well, if it is a hole, that means you have an x value as well as a y value, because a hole is a specific open dot on the graph. So let's have a look. How are we going to solve for the y value? Well, you take the 2 or the hole or the potential hole and you're going to sub it into the modified reduced rational function. Over here you got 2 plus 2 is equals to 1 over 4. So what that means is at x equals to 2, y is going to be 1 over 4, and this is not a point, but it is a hole on the graph. So let's look at another example here. So if you notice here, let's look at the restrictions. In this case, x cannot equal to 2. Okay, you have two choices. Either it's a hole or a vertical asymptote. And if you look at the top and bottom, we can actually reduce this and it becomes 1 over x minus 2. However, some students think that, oh, if you can sort of just cancel anything, I mean, reduce a factor, it's automatically a hole. But you have to be careful because, as I said, if there's a hole, you need to get a y value. So let's just substitute 2 or potential hole into here, and what do we get? We get 1 over 2 minus 2, which is 1 over 0. This is not a y value. This is actually undefined. So what does that say about this restriction in terms of what it looks like? It is not a hole because it didn't give us any y values. It is a vertical asymptote. So just to recap, review about vertical asymptotic behavior, when there is a vertical asymptote at a specific point, let's just say at A, there's only a couple of possibilities when it comes to rational functions. Either the graph could both go in the same direction, the vertical asymptote, or it can go down in the same direction, or it could have a combination of both. For example, it could go up from the left and go down from the right, or it could go down from the right and go up from the left. So that's actually 4 possibilities. So for this particular example, there is a vertical asymptote at 1. So here you have 1 and you have a vertical asymptote. Now the question is, how can you figure out how the behavior is? Well, in advanced functions, I think your teacher may have mentioned that, oh, you can substitute a small number to the left and to the right into the function and see what value that you get. So for example, if I subbed in, for example, a little bit to the right, so x equals to 1.01, the question is, what kind of y value will you get from here? In this case, I'm going to get a positive number, and it's going to be a positive big number, so it's going to go up. And if I sub a number to the left, like, for example, 0.8 or 0.9, I'm going to end up getting a negative number. And there's actually another way you can actually do this in regards to multiplicity. So when you have a square or a even degree function, I can tell right away that the vertical asymptotic behavior is going to be in one direction. It's either going to be going up or going down. You still have to like sort of sub in a number into a little bit to the right or to the left, and you'll determine whether it's a negative or a positive. In this case, because everything is squared and it's a positive number on top, I know it's going to be the vertical asymptotic behavior is going to go up. On the other hand, if the multiplicity of the factor in the denominator is a odd number, I know right away, based on what I know from my past courses, I know that this is going to be opposite directions. It's going to be going up or down, or the other way around, depending on the signs. And in this case, I know it's going to be this one here, because I'm going to sub in a number a little bit to the right, like for example 1.1. I'm going to get a positive number to the right. So in terms of notation, since let's talk about communication, let's use this example. So recap that we're going to be using limits to describe the asymptotic behavior. In other words, our asymptote is 1, and what this little positive means is it is to the right of the function, which is the y, and what's happening as you come from the right of the 1. Oh, you're going to be shooting to positive infinity. Vice versa, if you go from the other side, you're approaching the vertical asymptote from the left, from the left. So over here, you're going to be, the graph, the y values are going to go down. So this is just a recap of communication in regards to limit notation in regards to vertical asymptotic behavior. So let's talk about the end behaviors. So over here, the basic graph is 1 over x, and this graph looks like this. It has a horizontal asymptote over here. So in other words, the end behaviors, so they're using limit notation. So if I approach infinity, meaning I'm going to the right on this function, it seems like the graph is going to be approaching the horizontal asymptote. It's going to be 0. And vice versa, if I go to the left, I'll put here the left. So I go to negative infinity, what happens to the function? Well, it's going to approach the horizontal asymptote, and the asymptote is in this case going to be 0. So in this case, we're going to talk about horizontal asymptotes and also slant asymptotes, because they actually determine the end behavior. So we call it end behaviors are extreme left and extreme right. So just to recap, I believe that before that, we have a rational function. So let's just say you had a cubic over a cubic. To find the horizontal asymptote, all you do is take the leading coefficients of the function to give you the horizontal asymptote. In other words, if I gave you, for example, 2x3 over 4x3 plus 1. Well, because the cubics, the degrees are the same, we know that there's going to be a horizontal asymptote, which is in this case the leading coefficients, which is 2 over 4, which is going to be 1 over 2. Another one is, well, what happens if the degree is smaller in the numerator? For example, x squared plus 5 all over x3 plus 7. Well, if the degree is smaller in the numerator compared to the denominator, your horizontal asymptote is going to be automatically 0. And these concepts should have been explained in terms of algebra in advanced functions. So I'm not going to explain the details of why this is the case, because that should have been explained in advanced functions. Now what happens if the degree is higher in the numerator? For example, let's just say we had a cubic, for example, a cubic over a quadratic, for example. Well, in this case, because the degrees are different, has a difference of 1, we know that there's going to be a linear oblique asymptote of a linear, I'll call it a linear oblique. So how are you going to get this equation? Well, in advanced functions, you learn something about doing long division. So all you have to do is take x squared and you do long division, and you end up getting the following 0 minus 1. So in this case, you get x. So the quotient of the long division will become the equation of the linear oblique asymptote. So now we're going to start the calculus portion. So what I just talked about was the restrictions and the asymptotic behaviors and the end behaviors of what we did in advanced functions. So this part here is going to be the new calculus part, which we talked about in previous videos, critical points. So let's find the turning points and classify them, determine where the graph is going up and down. And this I haven't talked about. We'll talk about in this video the end behaviors of the slopes. The next one is talking about inflection points, so talking about the second derivative and figure out whether something is curving up or curving down. And we'll talk about the end behaviors on the concavity, which we haven't talked about before. We'll talk about here. And once we get all the calculations for all these three steps, we're going to bring it all together and graph it as best as we can. So here is a template, and this template is already posted on the Google Classroom document just to guide you of the steps. So first things first, again, we're going to deal with advanced functions. So figuring out the zeros, the restrictions, and the end behaviors. The second part will be dealing with just the first derivative. So figuring out the critical points, the turning points, the local max and min, and increase of intervals of increase or decrease. And the last part is we're going to deal with the second derivative function. So figuring out the where the second derivative is 0, maybe showing the intervals of concavity and inflection points. And then after we have all these three things, then we're going to graph it at the end. So let's have a look at this cubic over a quadratic. So based on what we know here, let's figure out the first things first. Let's deal with the restrictions. In this case, x cannot be 0. So but here, x cannot be 0. But the question is, what does that mean when x cannot be 0? Is it a vertical asymptote? Is it a hole? What is it? In other words, we're going to have to deal with something with the entire function. So I can see in the numerator, I can factor in x. All right, and then after that, I can reduce something. So I can modify this function and reduce the x's, and now we have this. Now the question is, well, what is this thing here? We need to address this. Well, I can tell right away it's a vertical asymptote because why? Well, if it was a hole, I should get a y value. However, if I take 0 and sub it into the modified, I end up getting 1 over 0, which is undefined, and right away I can tell it's a vertical asymptote. So we're done with the restrictions. Now let's figure out the zeros. The zeros come from the numerator. So in this case, I already factored the numerator. We can use this one or this one. It doesn't really matter which you use. I'll use this one here. Let's take the numerator and set it to equal to 0. But I know right away that when I bring the 1 over, I know that I cannot take a square root. So that means that this function has no zeros. Okay. And the last thing right now is, the second last thing is the vertical asymptotic behavior. So because I know that there's a vertical asymptote already, well, in terms of behavior, what is going to look like? So in other words, I'm going to have to figure out the limit as I approach the vertical asymptote from the right of the function versus to the left of the function. And I know because the multiplicity is 1, I know it's going to be opposite direction. So if I sub in a number a little bit to the right of 0, I'm going to get a positive infinity. Over here, if I sub a negative number into the entire function, I'm going to get a negative infinity. So it's it's opposite direction. And the last thing is the end behaviors. So let's have a look at the degrees. I can tell right away the degree of the top and the bottom are off by 1, and I know that I'm going to get a linear oblique asymptote. I'm going to put here LOA, or a slant asymptote, and I'm just going to do long division on this. Or if you wanted to, you can actually do the division for the modified one. You end up getting the same thing. I put x over x3, I get 0, and I bring down the x. X squared cannot go into x, so I'm done. In other words, this is my LOA is going to be y is equals to x. So we're done with the advanced functions part, dealing with the initial function, the original function. So let's deal with the critical points. In other words, finding the turning points or the local max and min. So we're going to have to take the first derivative. So we take the first derivative. You can use quotient rule or whatever techniques you want. And at the end, I'm not going to show you how I'm going to get the derivative. We end up getting this at the end. Or I'm just going to make it look more condensed. Okay. So let's find the critical numbers first. I shouldn't say critical points. You need to get the x values first. So we recall that to find critical numbers, you're going to have to look at the denominator and the numerator for the zeros. So we're going to set each piece equal to 0, and I end up getting x equals to positive 1, negative 1, and the denominator will give you a 0. So we have 3 critical numbers. I'll put here Cn. The question is, which out of these 3, which are points? Well, we know this one from the first part, that x equals to 0 is a vertical asymptote. So all we have to do is substitute x into the original function, and then we do that, so we're going to get, for this one, we're going to get y is equals to, and y is equals to something. In this case, we're going to get 2, 2, and negative 2. Okay. So once we get that, we're going to have to classify them as a local max or local min. So remember what we mentioned about, we can actually do a couple of tests. We can do the first derivative test, or we can do the second derivative test. I'm just going to do the first derivative test because I already have the first derivative and I didn't do the second derivative yet. So let's do the FTD. So what do we put in our first derivative? You need to put all your critical numbers, not points, but critical numbers from highest to lowest. So we're going to start off with -1, 0, and 1. And then you put f prime, and then you classify them. This I'm just going to dot because I know it's a vertical asymptote. This is a point. I'm just going to put here 0, 0 because the slope there is 0. And let's figure out the numbers in between. So if you sub in a negative, for example, a number to the left of -2, and we end up getting the following. And we end up getting the following signs. So let's make a conclusion right now. We can say that this one here goes up and then down. So it's a local max, a turning point. Vertical asymptote is not a point. And over here goes up, down, and then goes up. So we know this is a local minimum. The next thing I'm going to address is the interval of increase and decrease. Well, the FTD test, or the first derivative table, tells us everything. So here I know I'm going up. So anything below -1 to the left of -1 is going up. So here going down, anywhere between -1 and 0, this goes down. So 0 to 1 goes down. Goes down. And then this one goes up. Anything after 1 goes up. So this actually shows us the flow of the graph from left to right. End behaviors of slopes. So this is the brand new thing. So when I talk about end behaviors of the slopes, I'm talking about the end behaviors of this function, the first derivative. So let's have a look at the end behavior. So limits as x approaches positive infinity of this particular function here. Now going back to end behaviors, this is still a rational function. And if you notice, the degrees are the same. So what that means is I'm going to have a horizontal asymptote at 1 because leading coefficients are 1. So in other words, the limit of this function here is going to be 1. So what does that mean in regards to slope? So what that means is as you go to the right of this graph, your slope is going to be 1, meaning whatever happens in the graph, but at the end, the end of the graph is going to be linear, very close to a straight line. Vice versa, if I do the other way around, if I go to the left of the slope is also going to be 1, meaning somewhere down here, the end behaviors are going to be pretty linear, meaning the slope is going to be close to 1. And this calculation, actually supports the idea that there is a linear oblique asymptotic behavior. So we'll bring this all together at the end. Just to add on a side note in regards to holes, because in the previous example we didn't have a hole, but let's just say you did all this work and you had a hole. So when it comes to classifying and making your first derivative test, on your number line you have to include all your critical numbers, all your asymptotes, and all the restrictions. So in this case, you would include the -1 to 1. Vertical asymptote, you include the 5, and you also have to include the restrictions, which is at 3. So in other words, when you set up your number line, you have to include every single piece of information about your graph from your function in terms of restrictions and your critical points. So in other words, if I were to do this thing here, the table here, I know that this is a vertical asymptote, this is going to be a H, and these are our CPs, and then you can do your positive, negative, and start to classify them. So the next thing we're going to do is deal with the inflection points and all the concavity curving up and down, and that deals with the second derivative. So over here, second derivative, you're going to be using a quotient rule from the first derivative. I'm not going to show you all the steps, and we end up getting 2 over x3. So now we're going to have to find where the second derivative is 0 or undefined. Now look at the numerator. There is no x there, so we don't have any zeros of the numerator. However, there's an x in the denominator. X is equals to 0 is one of our critical numbers. And what are we going to do here? Well, the question is it a point? Is this an inflection point? Well, I can tell right away that we already established that x equals 0 is a vertical asymptote. It is not a point. So I don't think we're going to have any we're not going to have any inflection points based on our calculations here. However, we can actually work with the concavity. So we're going to do our second derivative interval chart, and we're going to include the 0 from the second derivative. this one over here, and you just do f prime, and then you just sub a number, and you end up getting the following. You're going to get, so this is a vertical asymptote, and over here, you're going to have a negative number and a positive number. So what does that mean in terms of concavity? This curves down, and this curves up. Now, just to recap, just because something curves down and up, it doesn't mean that this is an inflection point, because it does not have a y value. So the last thing we're going to do is talk about the end behaviors on the concavity. So what that means is very similar to before. We're going to have to look at the end behaviors of this function here. So of this rational function here. Or in other words, this is another way of saying what's going to happen to f double prime. So let's deal with this one here. Well, imagine you subbing a large number into this function. What's going to happen to the output? You're going to end up getting 0. Or for those that like to think, oh, the degree is a lot smaller than the degree of the denominator, you're going to automatically get an end behavior of 0. In other words, what this is saying is that the second derivative, as the graph keeps on going to the right, is going to have 0 second derivative, or we can say 0 concavity or no concavity. And what that means is, so as I said, we know that there's a linear oblique asymptote in this graph. So what that means is the graph is going to level off. Depends on whether it's coming from the top or bottom, regardless. But notice how the end behaviors is going to become very linear. And well, what kind of linear? Well, it has a slope of 1, like we calculated in the first derivative. And as the end behaviors are approaching to the right, what happens to the concavity? Well, it's going to be less concave, meaning it's not going to be that much curvature as you keep on going to the right. And we'll see that at the end when we put everything together. So here I drew out the vertical asymptote, which we got from the first part, and then we drew out the LOA. In this case, it's y is equals to x, so it's a 45-degree line passing through the center over here. Then we have our critical points that we had from our first derivative calculations. And we know the vertical asymptotic behavior. We know that it goes straight up from the right and then goes down from the left. So we know that piece of the function. And we already established that over here, that it curves down, and this is the local max. So in other words, it has to curve down. Over here, it's going to have to curve up. So I'm going to have to join this here and curve back up. And based on what we know that the end behaviors, so linear asymptotes actually dictate the end behaviors. And in this case, I know that this behavior over here has to approach the linear oblique asymptote. So I'm going to get closer and closer and closer. If you notice here, as I keep on going, it seems like the end behaviors is going to get very close to the linear oblique. In other words, the end behaviors is going to start to lose its curvature and become more linear. And when I say become more linear, it's going to approach the slope of the linear oblique asymptote, because this has a slope of 1. So over here in green, if I were to extend this over here, this part here is going to be kind of parallel to the linear oblique asymptote. Same thing for here. For the left behavior, if I keep on dragging this to the left, this part here is going to get very, very close, very, very close. It's not going to cross, and eventually it's going to be, seems like it's going to be parallel. In other words, this end behavior here, the left behavior, is going to lose the curvature because second derivative is going to become 0. And when you lose the curvature, it's going to become pretty close to being a linear. Well, what kind of linear slope? Is going to be close to a linear of positive 1, because the slope of the LOA is positive 1. And some people are wondering, well, Miss, how do you know whether the vertical, how do you know if the curve doesn't cross the LOA, for example, like this? It could, but I'm going to sort of save some work. So just a side note, and I think it's a good thing to point out, sometimes, you're right, the function here could actually cross and come from the bottom. In other words, which I didn't show because I don't want to extend the length of this video, but sometimes you might have to check whether the LOA intersects with the actual function. In this case, it doesn't, but in some cases, it will. So this is one piece here, additional piece, where you may have to check whether the graph crosses, because in this case, we don't really know where it comes from the bottom or it comes from the top of the LOA.